Hello, people. Welcome to week 8, Macam 101, section B1. Let us go straight to the exam. Okay, that's the wrong one. That's the right one. There we go. So these are the results. I blotted out these 4 individuals here because they did not write the exam and therefore do not contribute to the statistics of the exam. The exam was fair, considering that at least 2 people got up above 80 to 90%. One person almost a perfect paper. So the test was fair, and I know it was fair. I've been doing this for 28 years that I've been teaching this particular course. And that would have been the normal distribution, peaking out at about 65%. This is a small number of statistics. So it looks like the course, the test went nominally well. Now, the people around in here, these people can count on if they apply themselves, these people will pass. This person has a good chance of passing. This person has to work extremely hard, and this one even harder. All right. You just have to come and see me if you want a little help in trying to improve your performance. I can definitely help you, but you have to put in the effort. These people here put a little more effort, and you're guaranteed to be around C to C plus right here. That would be C minus, but as it exists right now, it's a fail. Okay, but I trust you're going to do better on the next exam. You now notice that I am very fair with the exams. Okay, this is right out of these first question right here. Prove that XOR is the dual of if and only if. We did that in the first presentation on the basics of logic, and it's right here. It's you just walk through it like we did. It's right there in the notes. Similarly, this was such an easy problem. It was right out of the notes once again. And these steps are right here. If you got it wrong, try and figure out what you did wrong. But I think the people that are at the high end of the spectrum probably got this right. Because, I mean, I said it was going to be on the test. I said this would be on the test as well. It's always on my first midterm. A variation of this. If m is an even integer, then m plus 7 is odd. You do it by direct proof, by contrapositive, and by contradiction. Now, you can't do this with every number theory statement. There are some statements that can't be done directly. They have to be done indirectly, and it's generally proof by contradiction. But this, again, is review. We did it in class. There's nothing new there. And I told you this was going to be on the exam too. I trust most people did well on this. You can run through this solution. We derived this in class. We derived A is not a proper subset. A is not a subset of B. I wanted you first stating A is a proper subset of B, and that's what it is right there, meaning that it is the same as a subset, but you can't have this equivalence. You can't have it's A is a subset of B and A is not equal to B. And so that's satisfied by this. And so the not proper subset thing can be derived through here. Basically, equality means it's a subset in one direction and it's a subset in the opposite direction. That is set equality. So that's what we have here. That's what we have here. We have A is a subset of B and B is a subset of A. And then you negate the whole thing and you arrive at this thing right here. That's the final statement. Okay. That means A is not a proper subset of B is as such. And here's some notes from ChatGPT that I decided to include as well. All right, this one is right out of that paper I kept telling you on Chinese remainder theorem. I repeatedly said that this was going to be, but just know it well, and that's a question right out of it. I didn't even modify it. So again, you should have got that right. Apparently, at least 2 to 3 of you really did follow closely what I was talking about. Others, the ones in the middle of the distribution around 50%, you still have a chance, pull yourself up. Now, having said that, Okay, let me just make something clear. I think I mentioned that I have an unwritten policy. It's an informal policy. Um, and in particular, it applies to this class. You people that have, not done so well on the midterm, you still have a chance of getting an A in the course, because in the end, I'm going to give everybody the same way of calculating grades. That is A, the overall distribution that was dictated by the introductory administrative PowerPoint. 25% for each midterm. There's two of them. That's 50%, 10% for assignments, which is just a joke. I know most of you, won't even do them. And then, of course, the final exam, which is 40%. I will give you, if you do really well on the final exam, I'll give you purely the final exam score. For example, if you did overall about a C minus in the course, but you did a B-like performance on the final exam, I'll give you a B. So I think that's fair. I think that gives everyone incentive to try harder, to do your work, and don't let ChatGPT do your work for you. So that's nice. All right. Okay, let's get back to what we were doing. Okay. Here, I want to try something on you. This is a nice problem, just to get us back into the mood of Chapter 6. Show that for all positive integers m and n onto m plus n, choose m equals m plus 1 onto m plus n, choose m plus 1. All right, that might look formidable. But this has been a problem on the final exam, so you might pay attention to this. How do you do this? Well, obviously you introduce the definition of the binomial coefficients, or at least the n choose m combinations without repetition. So we have n onto m plus n, choose n, equals n onto m plus n factorial over m factorial n factorial, just simply by looking at the equation. N choose r is n factorial over r factorial n minus r factorial. Okay, so we have that definition, okay, and that equals m plus n factorial over m factorial n minus 1 factorial. Okay, you can see how we just shifted things around here. Okay, that n got involved with the denominator here. Okay, so it's n minus 1 factorial, taking the n out and canceling it out with that coefficient out in front, or n at least, that variable. Now, let's go to the other side, m plus 1 onto this bit right here. If we expand it out, it's m plus n factorial. Okay, m plus n factorial over m plus 1 onto m factorial n minus 1 factorial. All right, so you can see we just simply plugged in these things, these two items, m plus 1 for n, m plus 1, m plus n for n, m plus 1 for that one. Okay. Now you know that this is combinations because we have the r factorial in the denominator, which makes the number of combinations much less than the number of permutations. You remove that, you get permutations. Okay. So that's right. That equals m plus 1 onto m plus n factorial over m plus 1 times factorial, times n minus 1 factorial. Okay, which equals m plus 1 onto m plus n, choose m plus 1, QED. All right, so that's how you do it. You just simply go to the definitions. It looks like an intimidating problem at first, but don't forget that all you do is just replace these in the basic formula as such, and just move on. So this m is r, obviously. Okay, so you get the idea. You see how to do that. That's a good problem. Okay, let's just move back now. Okay, hide. So we want now to bring up this one. Combinations with repetition. There we go. So this is section 6.2. Section 6.2. And here we are. And let's finish chapter 6 right now in week 8. So this is, oh God, I hate Adobe with a passion. Anyway, when something gets big, eventually it becomes corrupt. Adobe used to be so good. Anyway, never mind my opinions. This is combinations with repetition. Now let's do a little review. Okay, review permutations, combinations without repeating. Review permutations with repeating characters. Derive a formula for combinations with repeating characters and relate this formula to the integer solution of equations, which it happens to fit into, and also the so-called distribution theory. So this is chapter 6.5, section 6.5. I'm calling it 6.2. So here we call this was the general formula for n choose r as we wrote it in the back of that paper. All right. So now when you allow permutations to happen, well, you get rid of that r factorial in the bottom. So that disappears. So it's n factorial over n minus r factorial as opposed to n factorial over r factorial, n minus r factorial. R factorial is the number of permutations. Okay. So that we derived already. Now, here we claim this is, I'm calling it C prime. This is combinations with repetition rather than just P and C. I put a prime after them when I call them combinations of permutations with repetition. So I claim that it is n plus r minus 1 choose r. And we'll derive that and show how that works. When it comes to permutations, we've already seen this. It's actually not even worthwhile exercise to prove it, but we'll do it anyway. We did this when we were talking about bit strings, right? You know, you've got eight bits in a string, and that's a byte, you know, generally speaking. And since there's just a 0 and 1, and there's 8 of them, there's 2 to the 8. Okay, that is exactly this permutations with repetition. And you can see that's exactly what happens with an 8-bit byte string. So we've been using this already. Okay, it's intuitive, but we can derive it. So generalized permutations, combination 6.5. Let's go. So it's permutations with repetition, combinations with repetition, permutations with indistinguishable objects. So this is putting things into boxes, okay? Distinct objects into distinct boxes, indistinct objects into distinct boxes, indistinct objects into there's 4 of them. I just messed it up, but you get the idea. indistinguishable into indistinguishable, distinguishable into indistinguishable, indistinguishable into distinguishable, and distinguishable into distinguishable boxes. That's how it works. So here's an easy theorem. I'm not even going to prove it for you. This is, again, that's it. This is permutations with repetition. The number of R permutations of a set of n objects with repetition is n to the R. Okay, proof: there are n ways to select an element of the set for which there are R positions, like 8 bits. In the R permutation, where repetition is allowed, hence by product rule, there are n to the R permutations with repetition. And so we've already seen, okay, how this works, okay? How many strings of length R can be formed from the uppercase letters of the English alphabet? Well, there's 26 of them. So it's 26 to the R, okay? The number of such strings is 26 to the R, which is the number of R permutations of a set with 26 elements, okay? So we're talking in general about length R. So let's just go back and review. Don't forget the combinations has to do with choosing things in this order. So I can choose A, C, D, A, B, C, A, B, D, as long as it retains this order. It's not being permuted, okay? I think most of you know that already. So now we want to do this with repetition. By brute force, we have, when you have, you're choosing from 4 objects, 3 at a kind. That's 4 choose 3. Okay, that's the example we gave, of A, B, C, and we're choosing them now with repetition. That's what we get. Okay, all of these are in this order of A, B, C, D. Okay, they're in that order: AAA, ABB, ACC, ADD. So there are all of these, I think 20 or so: 4, 5, 6, 7, 8, 9, 10, 20. There are 20 combinations with repetition, choosing 4 objects, chosen 3 at a time. That's combinations. This is how we choose 3 letters. Yes, there are 20 such selections. In general, this approach is inadequate. We require a theory, so let us derive it. Okay, we don't have a way of doing this. All we have is n to the R, and then combinations, n factorial over R factorial, n minus R factorial, and then n factorial over n minus R factorial. That's all we have. So since that's all we have, with repetition, we're going to have to be ingenuitive. We're going to have some ingenuity, okay? So we have to work with the theory we've already developed. So we have somehow to, coerce it to produce this result, the existing framework that we have already. So how can we transform this problem into something already developed? It arises from the observation that we are not interested in arranging the chosen elements of the set A, B, C, D, and accordingly, they will always appear in the original alphabetical listing. Well, that's obvious. So the solution involves introducing a partitioning scheme. Anything to the left of the partition is an A. Anything between the first and second partition is B. Anything between the second and third partitions is C. Anything to the right of the third partition is D. So with 4 objects, there are 3 partitions. For A, B, C, D, there's a partition between A, B, B, C, C, D. Okay? So here we have it. Let's just say that the partitions are bars, and the A, B, C, we don't care. We just know that they're either A, B, C, or D. Okay, so here this is three characters at a time: AAA, ACC, ADD. This is how it would be represented with our new scheme right up here. Okay, so if everything's to the left of the partition, then these 3 stars are A's. There's an A, there's nothing, there are no B's, 2 C's, and no D's. There's no A's, 1 B, no C's, 2 D's. There we go. That's how this works. Recall that n equals 4 and R equals 3, choosing 3 letters from a 4-element set with repetition allowed. So your book does it like this. You can read it if you want. I think this right here makes a better sense. I mean, he complicates it with dollar bills and so forth. $1, $2, $3, $5. We don't even have these. We don't have $1 and $2 bills anymore. So look at this scheme here. I think this scheme is self-explanatory. So we've reduced the problem to a binary problem. There's just stars and bars. Come on. I mean, it's already solved. We already know what to do. So what we have here, the number of unordered sections of 5 objects from a set of 11. Okay, this is the number. Okay, well, let's go through it. Some possible ways of placing the 5 bills. The 5 bills being these. Okay, 1, 2, 3, 4. Oh boy, there's 6 bills. Some possible way of placing. Oh, 5 of the 6. Okay, 5 of the 6. So it's 5 choose 6. So it can be like this. So there's the representation that we came up with before. So there's no 1, no 2, no 5, tens, 2 tens, no 20s, no 50s, and 3 100s. Okay, isn't that what? Oh God Almighty! Anyway, it's these. So it's the same thing that we had developed before. This is the number of unordered sections of 5 objects from a set of 11. Hence, there are 11 choose 5, or 11 factorial over 5 factorial, 6 factorial equals. So we're back to the ordinary combinations with repetition, but with this newly formed arrangement of the different A, B, C, D, or these different dollars here. Here, I like this one better. So we've translated this into a binary setup, and that binary setup, is easily managed through the ordinary combinations without repetition. So we've derived it. So let's do that. We're claiming that n choose plus r minus 1 choose r is the same as n plus r minus 1 choose n minus 1. The number of R combinations from a set with n elements with repetition of elements is allowed is this, okay? So it's this. These are the same thing. That means they're symmetric. They equal the same thing. This is the one that I told you earlier that we were going to look at. So it's right here, wasn't it? Yes. There. That's what we said. These are distributions, but we're learning them as combinations with repetition. So there's that equation, and we're deriving it right now. Let's just do that, okay? So let's just do that now. All right. Oops. Okay. Okay. So proof. All right. Each R combination of a set with n elements of a set with n elements with repetition allowed can be represented. We're just formalizing what we just done. Represented by a list of n minus 1 bars and n stars. Or sorry, I'm so sorry. R stars. R stars. Remember, it's bars and stars. There's right. So it's n choose R with the stars. Okay. So the bars mark. Where am I? The bars mark the n cells containing a star for each time the ith element of the set occurs. combination. Okay. The number of such lists is Cn plus R minus 1 choose R. Because each list is a choice of the R positions to place the stars. And we just explained this. Okay. From the total of n plus R minus 1 positions. To place the stars and bars. Okay, for stars and bars. Okay, it's my shorthand. Okay, it's pretty obvious. So, in conclusion, this is also equal to Cn plus R minus 1 choose n minus 1, which is the number of ways. We just reverse the stars and bars. The number of ways to place the n minus bars instead of the stars. To place the n minus 1 bars. There. I mean, we already knew this without having to write it out. All right, we already knew this as we've explained it already. So, there we go. What's wrong with you? Come on, go away. What is this stupid thing? All right, there we go. So that's just basically what we just said. Okay. So all we have done in summary is we've converted the sequence of items that we're taking in combination and turning it into a binary system like this. A binary system which, when you use what we've already had before, when you use when you use this, that's this one, combinations n factorial over r factorial n minus r factorial. Now we can use this on our binary set, okay? So that's just the trick of hand, or the sleight of hand, that we've done. And we also note that it has the symmetry. It's n plus r minus 1 choose r, or n plus r minus 1 choose n minus 1. Here's where we're referring to stars. Here's where we're referring to bars. And there's n minus 1 less entities because it's the partitions go between elements. It's like a summation. A summation can have n elements, but it has n minus 1 additions between them. So they're like partitions, if you know what I mean. All right. So this one, you're not out there as a class. This is a problem to what will be on the second midterm. Something very much like this. So really know how to use this. Now notice here, this is different from what we learned without repetition. Here, k is assigned to 0. Then there's I sub 1, or it should have been ijk. I mean, here they've made it more general. So the I loop goes the for loop for I goes from 1 to n. Then it's nested here in the for loop for I sub 2, which goes from 1 to O. It goes to whatever this thing is here. So they're interrelated. Okay, it's just not a fixed figure here. It's this for loop is dependent on this for loop, and so on. Okay, and so when you work this out, that comes out to combinations with repetition. Note the initial value of k is 0. All right, yes. And that 1 is added to k each time the nested loop is traversed with a set of integers, all of I sub 1 to I sub m, such that all of these things fall in this order, okay, which is a given. The number of such sets of integers is the number of ways to choose m integers from 1 through n with repetition allowed. Hence, from the theorem, it follows that k, the number of what the number is going to show when it's all done, is n plus m minus 1, choose m. So remember how we come about this, because we have combinations with repetition in these nested for loops. All right? Just work on that if you don't quite understand it now. Just the trick between this and combinations without repetition is that they're not only nested, as in the problems that we gave for the product, the property of the theorem of God. My mind just went blank. I'm sorry. We have those rules, the addition rule, the multiplication rule. Well, the multiplication rule is nested do loops where they just go to a particular constant. Here they're referring to the previous do loop. So they're nested and interrelated. And so that produces repetition. And just by this reasoning alone, you can see that it just comes down to this. I'll never give you a problem that is harder than this one, okay? So please know how to do that. So here's another one. In the following program, segment I, j, k, and counter are integer variables. Determine the value that the variable counter will have after the segment is executed. So it starts at 10, and then the for loop for I goes from 1 to 15. The for loop for j goes from it's interrelated again, I to 15. And here for k, it goes from j to 15. So this is another problem for repetition. The moment you see a for loop that is related to a previous nested for loop, that it's nested within, that gives you the same kind of a situation we had before. That the reasoning that we had up here. Here, there are 3 nested for loops. That's R, okay? And there are between I, j, k, this ordering to 15. Okay, they're all 15. So we are making selections of repetition of size R equals 3 from a collection of size N equals 15. So there it is, 15 plus 3 minus 1, choose 3, is 17, choose 3. That's good enough right there. That's all you have to place. Although it does turn out to be 690. See, these are 2 different kinds of nested do loops or for loop problems that you should know. Okay. Oh, we can also look at this as the solutions to integer equations. So x1, x2, and x3 are integers. So we have x1, x2, and x3. These should be subs. Are non-negative integers. Each solution corresponds to a way to select 11 items from a set with 3 elements, x1, x2, and x3. Hence, by theorem 2, which is right? This is theorem 2. We know this is just simply the formula that we use for combinations with repetition. There are 3 plus 11, R plus N, okay? Minus 1, choose 11 ways, and 13, choose 2 is good enough answer right there. So this is the same as these nested for loops that are interrelated, is the same as this kind of integer solution problem. Positive integers, okay? Suppose that a cookie shop has 4 different kinds of cookies. How many different ways can 6 cookies be chosen? Well, solution. The number of ways to choose 6 cookies is the number of 6 combinations of a set with 4 elements. So you see, R is greater than N. Okay, that's a dead giveaway that it's combinations with repetition. By theorem 2, you just stick in the numbers and you get this. All right, so that is a trivial problem. Trivial. Okay. So in summary, we've got repetition allowed. No, yes. I mean, this just summarizes what I gave you in the beginning. Okay. So that's a nice summary. Here, now let's get back to that problem and proof theory that I gave you. I promised that we would show how it's done in chapter 6. And so remember that we're using 2 points on a circle and a line segment to bisect the circle. For example, no points, 1 area. 2 points, 2 areas. 3 points, 4 areas. 8, 16, womp, 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 31. Now, why is this the case? Why does this happen? It happens because in each of these cases, you are bisecting a previous area. There is a bisection, but once you get into 6 points around the circle, there is no way that you can completely bisect every area. It's just the nature of the geometry of the problem. I mean, that's a weak explanation, but anyway, the solution is this baby right here, 1 plus n choose 2 plus n choose 4. You don't have to know this. I'm just showing you there is an explanation of why it failed. It's something for you to be interested in, and that's about it. Otherwise, you don't have to know this. It's just to satisfy, the point that I said when I showed you that at the beginning of proofs, to show you that proofs were necessary for conjectures, because the conjectures could be wrong. Our conjecture was the number of areas is equal to 2 to the n minus 1, where n is the number of points. So next time, distributions. Okay, all right. Okay, so let's just pack it in for now. Tomorrow I'll give you the remainder of the chapter. Okay, that's enough for now, I think. Okay, all right then, people. It's a pleasure talking to you as always, and I bid you adieu. Bye bye.